Electrodynamics, Introduction to Electrodynamics, Chapter 3, Griffiths 4th edition. Let's talk about this. The whole chapter is about finding the electric potential. Okay? Because if you know the electric potential, we can find the electric field. It's negative the gradient of the potential. So if I know the potential all over all space, I can find the electric field all over space. That's a pretty easy thing to do. It's not even a difficult derivative. Well, it could be. But what if we have the charge distribution instead? Well, using Gauss's law, the differential form of Gauss's law says that del dot E, the divergence of E, is the charge density over epsilon naught. So if I put this in over here, I get del dot del of V equals negative rho over epsilon naught. So this is the second space derivative. We call that the Laplacian. So we can write this as del squared of V is negative rho over epsilon naught. Now, what we want to do is to solve this equation for charge densities. We're going to start off, it says right there, in empty space. So in empty space, this is 0. So we have this. How do you solve this equation? It can get complicated. But we're going to start off in this video alone. I'm going to solve this in a one-dimensional case. So in Cartesian coordinates, the del operator, which we call the Laplacian, is equal to the partial with respect to x, the second partial, plus the second partial with respect to y, plus the second partial with respect to z. Now, that's not always convenient. We may have sometimes to do that in spherical coordinates, which is much more complicated, but that's what that is. Now, imagine that I only have something in one dimension, in the x direction. So this just becomes the second partial of x. So I can write this as the second partial of v with respect to x is equal to 0. And that's the equation we're going to solve. Okay. So imagine, let's just do this equation. I'm going to do it here. And then in the next video, I'm going to show you how to do this numerically. So we have this. The second partial of v with respect to x is equal to 0. It actually turns out to be not so bad. There are a lot of different techniques to find the solution to a differential equation. This is a differential equation. But here, I can do the following. I can integrate both sides of the equation. If I do that, I get the first partial of v with respect to x is equal to some constant. I'll call it a. Right? Because you have to have that constant in there when you integrate. But it has a 0 there. I mean, I guess you could say I multiply both sides by dx. I skipped all that. Okay. Now I'm going to integrate again, and I get v is going to be equal to, if I integrate this, I get a times x. And then I have to add another constant. Let's call that b. So that's it. That's the solution to my electric potential in one dimension if there's no charges. Now, how do we find the value of a and b? And this is where we get the boundary conditions. So imagine that we have something simple. Let's say here we have our x-axis, and this is v. So at x is 0, v of 0 is 0. I'm just picking something to make it. Yeah, because we're going to use it later. And then v of 1 is equal to 2 volts. So we're up here. So this is our solution. It's a line. So in one dimension, the solution to this equation is a line. There's no other way to solve that equation, right? You can always go backwards. I can take this. I can take the second derivative with respect to x, and I get 0. Okay. And you can say, oh, well, if I just say v is 0, that's the solution, because if I take the derivative twice, I get the same thing. Yes, that is true. However, in that case, v is equal to 0 is a line, right? So still a line. Okay, that's it. I'm not going to talk about anything else. That's a short video. The next video, we're going to resolve this problem using the finite difference method.